Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. And this is lecture number 5, where we will be actually studying the energy band diagram, the Kronig-Penney model and the k-space diagram. Basically energy versus k-space diagram will be taught to you. Now let's see the outline of this talk. So at the very start, give you a brief introduction to what is the meaning of allowed and forbidden energy bands. Then we will look into the concept of how the energy bands are created when you bring two atoms or multiple atoms close to each other, right? And this is based on the principle that when you start bringing two atoms closer to each other, there will be an equilibrium position where your energy which is there within the system is minimum, and that will be the most stable sort of position where the atoms can be placed. So that formation of energy band we will be studying. Then we will be looking into what is known as a Kronig-Penney model for solids. We will also then go for k-space diagram. In k-space, how the diagrams look like, the energy band diagram, and then application of uncertainty principle, and then we will look into, again, just like the previous talk, differentiation between classical and quantum world in terms of operation of the device. So let's come to a basic concept here, and this is what I'm saying, you just take it for granted. We will come back to this when we actually study Kronig-Penney model and explain to you, or even before that when we discuss when atoms comes together. The idea here is for all semiconductors, right, you must be knowing it also, that we have three types of materials. One is known as a metal, one is known as an insulator, right, and another is basically a semiconductor. So if you look at the metal, then if I look at the energy band diagrams of metal and insulator, we'll see one by one. So let's look at the fact that when you define an energy band diagram, we have this conduction band, we have this valence band. Conduction band does have large number of free electrons which can participate in transport, right? It is transport. And valence band has large number of holes, right, which can again do a transportation. So if there are 100 electrons being created in the conduction band, there will be 100 holes available to you in the valence band, which means that if you are not doping or you are not doing anything, you are taking a extrinsic semiconductor and you are just supplying energy such that electrons from here can go to from valence band to conduction band, you will be generating equal number of conduction band electrons and valence band hole such that the electrical neutrality of the system is not lost, or total neutrality. So we define a conduction band where there are large number of free electrons available. We define valence band where there are large number of free holes available. Existence of electrons in valence band is not possible, and existence of holes in the conduction band is not possible. They are separated from each other by this gap known as forbidden energy gap, which effectively means that there cannot be any energy state of electron which will lie between this green line and the blue part. So there cannot be anything between this point and this point. So that is defined as the forbidden energy, means there cannot be any availability of electron in this region. This region is basically energy. So this is the energy scale on the y-axis, right? And x-axis is basically the distance, right? Okay. So basically, if you want to promote one electron, say from valence band to conduction band, then I need to give an energy equal to this much forbidden energy gap. Electron jumps to becomes free and leaves a hole here, right? So I have this conduction band, valence band, this jumps to this place, I have a free electron, I have a free hole here. Now if you apply a potential bias in this direction or electric field in this direction, the electrons will start flowing in this direction and the hole will be start flowing in this direction. This is a hole. This is the basic principle of a semiconductor system, right? So the energy required is equal to the forbidden energy gap. However, if this forbidden energy gap is very large, then the amount of energy required to promote an electron from valence to conduction band will be also very large, and therefore it might even sort of burn the substance even before electron becomes a free state, and that is known as an insulator. So if you have energy levels are more than 4 to 5 electron volts here, then we define that to be as an insulator. Semiconductors are those which have got forbidden energy gap, which is somewhere around 0.5 to 1.5 eV, or even less than that, 1.1 eV. This eV is the electron volt, So if you want to find the energy, you multiply this by 1.6 10 to the minus 9, 19. And in metal, interestingly, the conduction band and the valence band, so if this is the conduction band here, the valence band actually goes inside the conduction band. So what happens even at 300 Kelvin or even at very low temperature, there is always availability of free electron, and that's the property of a metal. Yeah, then you know that, because if you keep a metal even in room temperature, you do have free electrons available, and if you apply a bias, there will be flow of free electrons. So conduction band and valence band, they overlap here. So CB and valence band VB, there will be an overlap, right? In insulator, the forbidden energy gap is very large, and in semiconductor, the forbidden energy gap is relatively smaller, right? So this is the difference in terms of how much energy is required to form an electron hole pair. Now let's now come how these bands were initially formed or how they are formed. Now we all know that when electrons or any two atoms are very far apart, we assume that they will not interact with each other, right? The wave functions of the two electrons will not interact. So let's take this situation and let's look out. So I have a nucleus here, and I have a single electron system and hydrogen atom, and I have a nucleus here and there's an electron here. So this is a single electron system, typically an hydrogen atom problem, and they are relatively very far apart. When they are very far apart, right, the effective energy is very, very small. So if I plot, and this is where we are getting into, versus the distance. So this is the distance which you say, this is the distance, right? If you plot E versus X, then the graph comes something like this, right? Now X is the distance. So when X is very, very large, since the two electrons don't talk with each other, they are very far apart, there is no electromagnetic interaction, the energy is approximately very close to zero. However, when you start bringing them closer and closer, right, when you bring closer, there will be an attractive pull between the nucleus here and the electron here, right? And there will be also an attractive pull between nucleus here and electron of the first atom. This will be attractive in nature, so they will try to pull the two atoms very close to each other, and there will be also a repulsive force between this and this, as well as between this and this. One will try to bring them closer, other will try to push them further, repulsive forces. So when you try to bring X smaller and smaller, which means you're trying to bring them closer and closer, the energy starts to fall down. The total energy starts to fall down. It reaches to a minimum here, right? And then it starts to go up. Now you all know a minimum energy state is the most stable state. So what will happen therefore is the stable state will be when X equals to R naught. R naught is the distance. So we define this to be as an equilibrium distance between two atoms, where the probability of the finding the atoms is very large. Now we are assuming now from the wave function point of which we have already defined to you, that two atoms will interact, but their wave functions won't interact, and there will be no issues here. But when you start bringing them closer, one is the energy goes down, first thing, and there will be the energy levels will themselves split, right? So there will be discrete energy levels available to me as per the Pauli's exclusion principle. So you don't have a single level of energy, you will have multiple levels of energy, and that's what I've shown on the left hand side diagram here. So you already know there are 1s, 2s, right, 2p, 3s, 3p, and so on and so forth. These states are available, right? Now if I take 1s electron states, it has got, S has got 2 plus half minus half, 2 spins available to us. Similarly 2s will have 2 states available to us, but when they are very far apart, you see they are single states. When you bring them closer and closer and somewhere near the atomic distance, very near to the atomic distance, you see that they start splitting, the band starts to split, the band starts to split. And these are individual allowed energy states where you allow the electrons to stay. So we have learned two things. One is the energy minimum is defined as my equilibrium distance, which is R naught, where the energy is negative and bare minimum. And two things, when you bring them closer, there's a splitting of energy states happening. To showcase that, let me show you what happens when electron velocity changes by a small amount. So consider an electron which is traveling at the rate of 10 to the power 7 per centimeter. So, and we assume that the velocity increases by a value of 1 centimeter per second. If this is V2, right, and this is V1, then we can write down delta E to be equals to 1 by 2 mv2 square minus 1 by 2 mv1 square. which is equals to half m, we take common, v2 square minus v1 square. Obviously v2 can be written as v1 plus delta v, and in place of v2 we replace v2 by v1 plus delta v, and we get a v2 square to be equals to this much. It is v1 square plus 2v1 delta v into delta v whole square, right? So we already know that delta v is very small. So delta v is just 1 centimeter per second, whereas if you go back to the previous slide, this is 10 to the power 7 centimeter per second. So you can understand that delta v is very small as compared to v1. So what I can do is immediately I can remove this part, right? And finally we get delta E. So you see delta E is equals to 1 by 2 v2 square minus v1 square. So I can, v2 square can be replaced by 1 by 2 m, v2 square can be replaced by this quantity here. So that is v1 square plus 2 v1 delta v plus delta v whole square minus v1 square, right? This is what you will get. So if you move forward, what you get from here is that this v1 square will cancel with this v1 square. This is a very small quantity. You are left with 1 by 2 times v1 delta v. So 1 by 2 m into 2 v1 times delta v. So this 2 will get cancelled with this 2, and you are left with mv1 delta v. So the change in the energy when you move from a lower velocity to a higher velocity is given by mv1 delta v, right? Now if you substitute the values of m, v1 and delta v, I get delta E to be equals to 5.6 into 10 to the power minus 9, which means that if there is a 1 centimeter per second change in the velocity, absolute velocity of the electron, the change in the kinetic energy will be 5.7 10 to the power minus 19 electron volt. You want to convert into joules, you multiply this 5.7 10 to the power minus 9 into 1.6 into 10 to the power minus 19 joules. So that you see it's very small quantity which you get. If you get minus 28, this will be the order of 10 to the power minus 28 joules. So which means that if electron is moving at very high speed, increasing it by a small quantity does not change the overall energy to a larger extent. So this is just a methodology to show you, and we will be using it time and again later on. Let's take a silicon atom. That means I have multiple silicon atoms lying, and I try to bring them closer and closer till the interatomic distances becomes equal to the equilibrium distance, which is R0. So there are 14 electrons. Since the atomic number of silicon is 14, there will be 14 electrons available, right? And so they will be all shells which are available there. So n equals to 1 will give you 2 electron state, n equals to 2 will give you 10, so 10, and the last shell will give you the 4 electrons in a sense. And therefore silicon does forms a catenation sort of carbon because there are 4 silicon valence shells. So this is the valence shell which you said, and the core shells are this and this. So you see the valence shell is relatively weak, whereas the 4 electrons which are available in the valence shell are weakly bounded, and they only involve in the chemical reactions, whereas the bonded states, about 10 in number, they don't take part in any of the interactions with other atoms. Now you must be aware that S state, so we know that there are S state and P state. Within S state you will have plus half and minus half. So there are 2 electrons which are available. Within P state you will obviously have Px, Py and Pz, and each will have again a plus minus half, and so on and so forth. So there will be 6 electrons associated with P type electrons. So please understand that S will have 2, P will have 6 electrons available to us. Now let's come to the fact that you are now trying to bring the 2 atoms close to each other, and as a result you see the same diagram which I had plotted earlier. I'll just show you where. This is the plotting which you do. So we get R0 here, and if you can see at this one, you have a minimum energy scale which is negative here. Just take this into consideration and look at this one. So outermost shell will have n equals to 3. N equals to 3 will have S and P, and that's the reason you have 3S here and 3P here. When they are very far apart, you don't see a splitting of the bands. They are single bands available to us. 3S state will have 2n electrons. Suppose there are n number of atoms. Since each S state will have 2 electrons, there will be 2n states and therefore 2n electrons. Whereas if you look at P type, P has got 3 and there are 2n electrons available, then there are 6n states available. 6n states, why? Because P shell has got Px, Py, Pz, and each will have 2 states, and therefore total will be 6n states, out of which 2n states will be occupied by the electrons. Now you start bringing them closer and closer implies that I am bringing it to the left hand side. I am bringing them closer and closer to the system. Somewhere down the line, when your R value goes down, you see these energy bands starts to split. And how do they split? They split in a fashion such that equal number of states are visible to the top and bottom. So there are 4n states available here, and there are 4n states available here. But the interesting point is, since there is always a requirement that everything should be occupied in the minimum energy state, all the available electrons, both from P and S, all get occupied in 4n states. So therefore, in the energy scale, when you go down, if there are 4n states, right, then there are 4n electrons available. So all the 4n states are fully filled up with electrons. Whereas if you go to the top layer, there are 4n states agreed, but then there are only 0 electrons. So all are empty. So the top one is known as conduction band and the bottom one is known as the valence band. So even at T equals to 300 Kelvin or low values of temperature, we assume that all the states of valence band are fully filled up and all the states of conduction band are fully empty. And the distance between the two, the energy at A0 is the equilibrium energy at equilibrium distance. At that point, the difference between the two is basically equals to Eg, which is the band gap, which we already seen. But what about the takeaway of this discussion? The takeaway was that when the electrons or atoms are very far apart, they don't interact, bring them closer to each other, there will be an equilibrium value of distance where the energy will be bare minimum. At that particular point, a stable electron will be situated, and if you bring them further closer or near that point, there will be band splitting, one higher band and lower band. Lower band will be fully filled up with electrons because of high stability, but the higher band will be fully empty. The higher band is referred to as conduction band and the lower band is referred to a valence band. So this was the basic idea, and we therefore end up with the principle that I have a conduction band, valence band, and there's a forbidden energy gap for any system which is available to us. It is just that in semiconductor, the distance is relatively smaller so that there can be easy conversion from lower state to higher state. Now, about quite a decade back, about a century back, Kronig and Penney gave a model of solid state. So in solid state, if you remember very clearly, that atoms are situated in solids, especially latticed solids, the atoms are situated in such a manner that they are, say, at a distance of x from each other always. And if it's a three-dimensional crystal, then you will have x situated along this direction as well. So this is x. If we talk in two-dimensional, this will be two-dimensional. Three-dimensional means basically inside this your laptop screen there will be third dimension which is there. So this is a three-dimensional such that the distance between the two atoms are always constant. Plus, but please keep in mind that if I plot the potential function, and let us suppose my atom is occupying somewhere here, this is the stable position of the atom. As discussed earlier, the energy will be actually behaving in such a manner that it will be almost zero here and will go down as you so potential will go down as you move down and becomes very large value of negative near the edge of the atom space wise. So, and this variation of energy is 1 by r. So this variation of not energy potential is equals to 1 by r, proportional to 1 by r. Proportional to 1 by r basically means that as you bring the value of r smaller and smaller, negatively the value of v of r will go on increasing, and this ends up having a stable state available to us near the atom. Now if you take this for a single atom and then try to sort of extend it to multiple atom states, then the figure which you get is on the right hand side at the below. So I have v equals to 0 of profile, and then I have atom number 1, atom number 2, atom number 3, atom number 4, and the potential variation is shown in the manner shown here, which is very important, that therefore the electron energies at the atom, total energy of the system near the atom, is negatively large, but when you reach away from the atom, somewhere in the middle of the two, you will actually see that the value of the voltage is nearing 0. These two potential belong to atom number 3, this is for atom number 2, this is for atom number 1, and this is for atom number 4. And it reaches a minimum near the nuclei of the atom and becomes maxima away from the atom, and near the next atom it becomes maximum. So this is a potential sort of a diagram for the Kronig-Penney model. Now what later on, I'm not doing the mathematics here, but what Kronig-Penney showed was model showed was that the electrons can occupy only certain energy bands or certain energy levels. They cannot continuously be in the energy scale. So either they should be in E1, E2, E3, or E4. And it came from the fact that if you look very closely, if you just look at this, it is almost like a potential well. If you see, right, at this particular point is a potential well. In a potential well, you discretize your energy states. The energy states are discretized, right? And the distance between the two energy states is actually governed by the distance of the potential well and the height of the potential well, which means that if you start making the atoms behave in such a manner that they are very close to each other, my let us suppose this is A, then A value will go down and the band will start splitting more further. If you make it further apart, the band splitting will actually reduce drastically. So this basically, the Kronig-Penney model shown at the top, is been explicitly emulated by this statement at the below, that now if you see very cleverly, at point X here, you see, at point X here, you have the minimum energy in a sense available to you. And then if any electron is available here, it sees a barrier here, energy barrier here, and that is being emulated by these barrier potentials here, right? So if you take full Kronig-Penney model, then it is basically nothing but square wave potentials which are getting in a periodic function in a manner shown here. Now let's come to the k space diagram and then we'll come back to Kronig-Penney model. If you plot k versus E is basically energy, which is half mv square, right? And this is also written as p square by 2m. Then we can write down the energy to be equals to p square by 2m, where p is the momentum of the particle. Now if you plot E versus k, then this is k or p we can write down. When p equals to 0, energy equals to 0, which is correct also. If there is no velocity and it does not carry any momentum, obviously its energy will be equals to 0. But as the momentum increases, energy increases in a parabolic capacity, and that's what you see the dotted line here. This is known as an EK diagram, right? This is also referred to as an EK diagram in solid state semiconductor theory or solid state theory. This is known as EK diagram. So this graph gives me an idea that if I a priori predict the value of the momentum, I could predict the value of the energy which is contained within the particle at that particular value, right? And that gives me a proper way of figuring out what is the energy if the momentum or k vector is known to me. Now after solution, you will not get this, you can get it from this book, the whole derivation. But after the solution, if you plot a quantity, so this, what is A? A is basically your this distance, this is B and this is A. A is the separation between the potential barrier and B is the value of the step potential of the function itself, right? And you get this is A and B, and we are starting from 0, we are assuming it to be true. Now if you plot it and if you do small amount of simple mathematics, then if you plot this function with respect to say alpha of A, then it looks something like this. It's basically a sinusoidal but damped sinusoidal as you move across alpha. So you see this is getting damped, the peak of the potential curve is getting lower, it will go lower and lower as you move across. So at pi you will have this value equals to 0. You can do it yourself. In fact, at pi, 2 pi, 3 pi, you will always have 0 values of this quantity, and you will have maximum values at 0, at 3 pi by 2, and so on and so forth, which basically means that the maximum and the minimum value of p prime sine alpha a upon alpha a will be found at certain places. My job is to also now plot cos of alpha and then add the two terms together to see which of the eligible states are available for the property of conduction. This is how it looks like therefore. Now if you plot cos of alpha a with respect to alpha a, it looks something like this. And these are very pure mathematical expressions. Now what you need to do, you need to add these two terms, right? From where I am getting these two terms at this stage, we won't be doing it. Assume that the equation, Schrodinger equation, has been solved, and after solution I got this term p prime sine of alpha a upon alpha a plus cos of alpha a. Now we plot individually this p prime sine of alpha a upon alpha a as well as cos of alpha a, which is this one, and then we try to add these two together or superimpose these two together, and this is what I get. So the entire function is represented by these things. And if you be very careful, if you remember that the maximum and the minimum value of f of alpha can go to +1 to -1, right? The maximum value of alpha, f of alpha a, the function which is on this side, obviously can be +1 or -1 because it is made up of sine and a cos. And you know what is the maximum limit and minimum limit of sine and cos. So you cannot go beyond that in any case. So you means the allowable area. So if you look carefully, this dotted line which you see are the boundaries, and we have plotted here that expression, the expressions which you've seen here. What are the expressions? This is the expression which you have, this and this. If you take them together, we get this, right? Once you get this, you just need to find out the crossing points. So these are the crossing points here, right? These are the crossing points here. What is the crossing points? Ka equals to 0. At ka equals to 0, I will get this crossover point, and then at ka equals to pi, I get this the crossing point, right? So when I get ka equals to 0, I get the first crossing. Ka equals to pi, I get the second crossing, and then ka equals to 2 pi, I get the third crossing, and then ka equals to 3 pi and 4 pi and so on and so forth. So we will get like that, right? And alpha a, this is alpha a, this is alpha a value which you get, right? And so you see the curve, which is the blue curve, which is moving from this point to this point, is going from +1 to -1 at this stage, and therefore the effective allowable states are only these one. Similarly, the effective allowable states are this one. This is the effective allowable states. So what I have come to prove from this Kronig-Penney model is that not all the states are allowed in case of using Kronig-Penney model. Only few states are to be allowed, and these states are governed by the underlying equation which is shown here. So let me recapitulate what we learned from all these lecture. And the lecture which we learned was that we understood what is the meaning of equilibrium potential, what happens when two atoms are very far apart brought together, how the band splitting takes place, and what is the meaning of conduction band and valence band, and how many states of valence and conduction band are fully filled and fully empty. We also learned to see and distinguish between semiconductor, metal, and an insulator. And finally, we ended up that material, if you have material which is silicon material, let us suppose, where atoms are arranged in a regular fashion, then if you want to see the energy scale, the energy scales are always discrete in a sense. They are never continuous. So we have learned that discreteness depends upon the dimension of the potential well, right? So we know the difference between semiconductor, metal, insulator. This is one thing. We also understood about equilibrium potential. We also understood that the discreteness comes from the dimension of the potential well. And finally, we also saw the EK diagram, and therefore a priori I will be able to predict the energy if I know the momentum of that particular space. And the last point which we learned was, using Kronig-Penney model, we learned that there are only certain allowed states where the energy of the material is allowed to do that, right? So this gives me a brief idea about the fundamentals of semiconductor in a sense, and states that discrete energy states are available. So we have understood equipotential, we have also understood the meaning of semiconductor, and we have looked into the discrete energy states. So with this, we end up today's lecture, and thank you for your patient hearing.